Hi, hello, and welcome to the intimate section number 8. So, let's talk about announcements. Announcements. I'm doing mid-semester meetings. Well, so it doesn't work for the people in the room because it's only ASMR if you're like listening back to it. But otherwise, it's just whispers. Yeah. Yeah. Also, like when I do hold it here, it does like blow out the mic. So. Mid-semester meetings are happening. They're in the Smith Campus Center by the Mother Juice, opposite Holyoke. Big glass wall. Already had several meetings. It's been fun, fancy, and I'm looking forward to chatting with y'all, I think. Yeah. And now I think I'm looking forward to it. It's like, I know I've met with y'all, and they were great, and I'm looking forward to meeting with y'all. Mid-semester feedback, so thank y'all. Y'all were very kind. My gosh. Lots of things. Maybe I'll respond to some of the feedback of things to change. Like one of them was about section videos being posted sooner, which they're just super large file sizes, and so because they are so big, if I'm going out of town on the weekend, it often doesn't get posted until Monday. But the 2024 videos are up on Canvas completely, and it's really, really close to what's happening. So you can always watch those if the 2025 ones aren't posted yet. So they're in the general information tab, right the top module on Canvas, and there should be one for the 2025 and 2024. Yeah, totally. In terms of things to change or things that y'all would like to see different, it's really hard because there are lots of contradictory things. Some people are the problems in section are way too easy. We need to be working on harder problems together, exam level problems. And then some people are working a challenge problem in the last 20 minutes is not worth it. By that point, I'm checked out of section and it's too long. So let's not work the hard problems. And then some people are I want more time to work on my own on problems before we go over it together. And then some people are giving us time to work on it in section is useless. We should only do guided problem solving because that's going to be more time effective. Also, at least 10 people said section should be longer, which is crazy. Crazy.
Because we love section. Seriously, it helps so much.
Oh my gosh. Y'all were very, very sweet. People like the Pavlovian conditioning and the little mnemonics. And the notes is the most commented on thing in the entire feedback. I fed the feedback to AI and I was summarize some results for me because I read through everything, but also I wanted to count things, how many times did it say section notes or whatever. Section notes were mentioned 28 times of it was helpful, which I'm glad because in my mind, I like it. It's I have a passion for graphic design, but it's also kind of ugly because it's so crowded. It's so maximalist that yeah, but I think it has to be kind of busy in order to be helpful with the information. Cool. So that's most of responses to mid-semester feedback things. Meetings. Today we're going to be talking about the alkene reactions from lecture 8. The radicals that you started at the end of lecture 8, I'm going to cover at the beginning of section 9 and Friday. So we are going to talk about it, just not today because it's kind of a different beast. I like to divide up alkene reactions into simple reactions and complex reactions. So we'll kind of talk about those in a little bit more depth in a minute. And then at the very end, the last 10 minutes, we'll talk about the Wittig reaction. So that's kind of big overview. But to start off, I'd like to show you my magnum opus. Yes. There's a Drag Race meme that's before we begin, I'd like to give you a few moments to compliment my hair. And that's how I feel about this diagram of yes. I love it. I love it. Because it is a lot, but the colors group it into families to help make it a little bit more chunkable. And the families all have the same mechanisms or type of reaction that's happening. So that helps kind of divide it up a little bit. Then it's not drawn on here, but one way that I think is helpful to think about it is imagining some dividing lines here. So almost halfway, where everything to the right of this, I typically call the simple alkene additions. And to the left, I call the complex alkene additions. Now, I know that feels okay, more terminology or whatever. These are my made up things to help make it clear what's important. In the simple alkene additions, we care a lot more about the mechanism and like how the reaction is taking place. Whereas in the complex ones, we care much more about the line reactions and just generating the product. So I think for the simple ones that we covered today, we're going to be talking a lot more in detail about the mechanism, but the complex ones, I'm just going to touch on a few features for like line reaction studying. There's also like a color ombre of like the red family has the like slightly darker red box that does all the mechanisms and things, and I love it. So, thank you. So to start off, we need a transition. Alkene terminology. With each of the alkene reactions, we have some logistics that we have to cover. We have to learn when we are studying the actual reactions that were presented in class, essentially. So there are 3 questions that you need to be able to answer for every reaction that we taught you for alkenes. It is the what, where, and how of the reaction. So the what is what 2 groups are added to the alkane. So like for H3O+, you need to be able to clock that that reaction adds an OH and an H to the alkane. For Br2, what does that add to an alkene? Br and Br. So it's just the kind of what gets added. And 2 things are always added because we need to replace this double bond, like both carbons will need a partner afterwards. That is the what. The where is a question of regiochemistry. So regiochemistry is which region of the molecule is reacting. And most of the regiochemistry for these alkene additions follows Markovnikov's rule. Our version of Markovnikov's rule is the more electronegative thing is added to the more substituted side. So I think about it like more together. There are different ways of phrasing this Markovnikov rule, and so if you look at other textbooks or outside resources videos, they might say something like the hydrogen adds to the less substituted side. That lines up most of the time, but our definition is a little bit more expansive, as we'll see in some of these niche cases. So Markovnikov's rule, the more electronegative group adds to the more substituted side. Well, the more electronegative thing is typically some sort of nucleophile, and the less electronegative thing is typically a hydrogen, actually. So we are doing our Markovnikov product, looking at this alkene, which side number 1 or side number 2, is more substituted? 1 is more substituted because it is printed on the page, but also because this side has one thing attached to the double bond that's a carbon and then one that's a hydrogen, whereas this is just hydrogens. And so by substituted, we mean like connected to other carbons. So this is an asymmetric alkane. If we had something like this, it's equally symmetric on both sides, in which case we can't choose a more substituted side, right? Another one is like, what about this? Is there a more substituted side? No, it's going to be the same on both, so we can't choose. Like, we're going to get a mixture of things. But here, for the more substituted side, we add our nucleophile, the more electronegative, and the less substituted side, we add an H, and that's our Markovnikov product. Sometimes, however, we're going to want to build molecules where we add our nucleophile to the less substituted side, and in that case, we need to get the anti-Markovnikov product. So Markovnikov or anti-Markovnikov are our regiochemistry terms. That is the where. Last logistical question, the how. The how is talking about stereochemistry, the relative orientation of the 2 things that you add. So if your double bond is like here, you could have added the 2 things both up or both down, in which case we call that syn addition. Syn is on the same side, so like both wedge, both dash, or you can think about it 3D as just like up or down. The other way that you could have added is if your double bond's here, one thing could add up top, one could add at the bottom. And so you have anti, and then you have the other version, anti. And we can also visualize it here. So now we have a dance, the syn and anti dance. So syn, anti, anti. Are we ready to try it? 1, 2, ready, go. Syn, anti, anti. I imagine that this should become our classes, like, do you know the meme of the Camp Rock? Yeah. And they do the like little pattern. Y'all, if you are like crossing Harvard, y'all, and see each other cross, go. Yes, and everyone will be like, what cult is going on? They'll be like, mysterious. Now, there are some reactions that don't have a preference for syn or anti, in which case we're going to get mixed. So I am accepting suggestions for the dance move for mixed. The best one that I've gotten so far would be syn, anti, mixed.
Oh.
Just because she's a little, I don't know. So if you have a better one, let me know, and we'll try it out. But now, this whole syn and anti question can sometimes just be irrelevant. So look at her, this reaction. We've added R1 and R2, just whatevers, to this. Is this a stereocenter? No, 2 methyls. Is this a stereocenter?
No.
2 hydrogens. So we don't really have any stereocenters, so we don't need to even worry about syn or anti because there's nothing for us to show. So it doesn't matter. It only is going to matter when we have stereocenters, and we can have up to 2 stereocenters created, which is annoying. The other warning, ANTI, we see here in syn and anti, and we also see it in anti-Markovnikov, and they mean different things. This anti means not Markovnikov. This anti means on opposite sides. So just the same letters appear, but they are different. So our 3 questions, the what, where, and how. What I've done on my little ring, what, where, how, for all of them outside. So just go ahead and do that analysis and make it easier for you to study. So we're about to talk about the acid addition family here, and the what is a hydrogen and then something else. The where is Markovnikov for all of them, and the how, we're going to get a mix of syn and anti. That's done for all of them. So hopefully that will make it a little bit easier to study. But each of these reactions that we were taught in lecture, you need to know the answers to those 3 questions in order to be able to accurately get the results. Work? So let's jump into it. I know, lots more. So our first family that we're going to talk about in the simple alkene additions, there are 3 that we're going to kind of zoom in on, are acid additions. Acid additions always have acid present. And so the first step is always going to be your alkene going and grabbing a proton. Now, this could be from HCl or HBr, or we could have acid and H2O or acid and an alcohol, in which case it would be like, this is H3O plus, essentially. So in all of them, no matter what our kind of X is here, we are going to grab a proton first, and we have options to which side that we put it on. And I'm so sorry, this has a little typo in that there's supposed to be a methyl here. So over here, we could add the hydrogen on the right side and make a carbocation on the left, or you can add a hydrogen on the left, make a carbocation on the right. Which one's going to be more stable, option 1 or 2? 1, because we have a tertiary carbocation versus a primary carbocation. So we know hyperconjugation is going to stable that tertiary one a lot more. Okay, so that's what we get. We've added the H. And then we have an MTP orbital carbocation, and whatever else is present, so like the Cl minus, the Br minus, the H2O, the alcohol, can go and attack that MTP orbital for the second step. And now we have added our 2 things, so a hydrogen and then some other nucleophile. Now, when you do this, there are kind of 2 tricky things about it. So the first one is we formed a carbocation. What can carbocations do? Rearrange. They can do funky things. So if you were trying to add your alcohol right here, you're going to look like Boo Boo the Fool because a 1,2-methyl shift happens. So what you have to do, or what I do in order to minimize mistakes, is anytime, even in a line reaction, when you are doing an acid addition to an alkene, draw the carbocation intermediate just as a check for yourself to ensure that there's no rearrangement. Because you don't want to miss, like, on 1 or 2 points nickel and dimed on the test just because you forgot to check for a rearrangement, you know? So these carbocations can be a little bit sneaky sometimes. So that's one of the challenges of this family. And the other challenge has to do with the stereochemistry. This is the most complicated version you would ever see, and I wanted to do the figure here, the most complicated version, because oftentimes it will be easier than this. But let's talk through it together. So, first of all, does everyone remember deuterium? She's the isotope of hydrogen. She reacts exactly like a hydrogen. So, if we are thinking about, okay, we grab a hydrogen, we could either make a carbocation up here or up here. Well, this thing is like a hydrogen, right? So is this a primary or secondary carbon or tertiary carbon? Secondary, because this D is just like a hydrogen. This is tertiary. Which one's going to be the more stable carbocation? Tertiary. So in both cases, our carbocation is at the top, and we have added the hydrogen at the bottom carbon. But if our double bond is here and our acid approaches from the top, then our hydrogen's on a wedge. Versus if our double bond's here and our acid approaches from the bottom, it's on a dash. So already we have two options for things that could be happening. Then, once we have an empty p orbital, one thing that we talked about with SN1 reactions is our nucleophile could either attack the top lobe of this orbital, or it could go and attack the bottom lobe. And so we're going to get two options for each of these carbocations. So like here, this is the version where the H is on the wedge for both of them. And we could have the nucleophile attack from above on a wedge or below on a dash. Same thing down here. These are where the H was originally below, and the nucleophile can either attack from below or above. Now, if it forms four products, you need to indicate that four products are formed. But we can do some work smarter, not harder things. Essentially what we need is every combination of wedges and dashes for the two things that we've added, right? We need the wedge, wedge, dash, 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 wedge, wedge, dash. We need all four of those combinations. And we can use our knowledge of enantiomers to help us save us some drawing. So remember enantiomers for diastereomers, enantiomers, non-superimposable mirror image, enantiomers, clap, 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 all swap. So what is the enantiomer of this one? Is it 1, 2, or 3? 1, all swap. And so instead of drawing both of these, I could draw one of them and put plus minus. And that indicates, hey, the enantiomer is also present of this molecule. And then you can do the same thing over here. So this one would be the syn one. And you can also, as your second thing that you draw one of the anti ones. And then for each of them, if you put a plus minus, you could just draw what's in the blocks, and then you've generated all four products. This communicates to us with the plus minus the exact same thing as writing out two separate structures for each. So that is the kind of hack way of doing it. Draw a syn version, draw an anti version, and put plus minus for both of them. Warning. You can't just put a plus minus willy-nilly, because it means a very specific thing. It means the enantiomer. So if you place a plus minus on the test, and plus minus is not relevant, that is like minus 0.25. I'm so sorry. I'm so sorry. I'm so sorry. So yes, use the tool, but only use it when it's appropriate, because otherwise we're just throwing things out hoping for the best. So last thing over here, I've just listed out the 4 specific reactions in this family. So all of them, they add H as one of the partners. And then our X group is either going to be a Br, a Cl, an Or, or an OH. We stumbled into another way of making ethers. I hate it. Yeah, really horrible. Worst functional group, thank you. Yeah, so without further ado, let's try to figure it out. So let's look at practice 1 over here. And for practice 1, I have made these 2 alkenes and given you a reaction. And I think first step, figure out the what, where, and how for these specific line reactions. What's being added, where is it added. Second step, draw the carbocation, check for rearrangement. And then third step, make sure you're generating all the products. If you have 2 stereocenters, you're going to have a total of 4 products. And remember, you can use your plus minus tricks. If you have 1 stereocenter, you're going to have 2 different products. So I'll give you a few minutes to work on that, and then we will jump into it. Ding dong, how we doing? Can we talk about it? So, first up, what two things are added with H3O+. H and OH, great. So now we add the OH to the more substituted side, so it's going to be added here, and the H adds here. But always as a check, we want to draw our carbocation intermediate just to see. So if we add the H to this side, there's already an H there. So is this a stereocenter? No. So we can't get 4 products. At most, we can get 2. And here we have a carbocation. Is this carbocation going to rearrange?
No.
But it's next to a quaternary carbon. Is it going to rearrange? It doesn't rearrange. So remember, we have to think why. The only reason it's going to rearrange is to make a more stable molecule. If we did a methyl shift here, we're just going to make another tertiary carbocation. It's not going to be more stable. We're not alleviating a ring strain. So why would she rearrange? She wouldn't. She wouldn't. So, sorry, I was trying to really, push you. So, with this, we have our empty p orbital. We know our OH, like our water, can either attack from the top face or the bottom face. So, I'm just going to draw a version of the product where, let's say, I'm going to put the OH on a dash. Whatever, it doesn't matter. And then I add my plus minus to say I also have the version where it adds on a wedge. Also, that's a crazy looking terbutyl. It's still crazy looking. Anyway, but that's the answer. Then the other one, we are going to put our carbocation on the more substituted side here. We're going to put our H on the less substituted side. And then with this, is this a stereocenter? Yeah, and then when we attack this, we can attack either lobe. Is that going to make a stereocenter? Yeah. So just based on doing that, nothing else, like when I draw the carbocation intermediate, I don't draw wedges and dashes, and I ask myself about the stereocenters. Just because if I know there are 2 stereocenters, how many total products do I have to have? 4, because we're going to get a mixture of everything. So what I do is I don't even think about actual mechanism things. I think, okay, there are going to be wedges and dashes, and I need to get every combination. So let's do that. So version 1, I'm going to put the hydrogen on a wedge that I added, and then the deuterium on a dash. And then I'll put, what 2 things are added by HCl? Yeah, well, ding dong. I'll put the Cl on a wedge, and then the methyl that was already there on a dash. So again, when I draw my first one, it doesn't matter. I just need to make sure I get all the versions. This one, is this my syn addition or my anti addition? Syn, because both the things we added are on the same. So if I do a plus and minus with it, that's going to give me my other syn product. So now I just need to make sure I draw a version that's anti. Okay, so I'm just going to keep one of my stereocenters the same, and then swap the other one. So now the 2 things I've added are H and Cl, and they're anti to each other, and if I do plus and minus, that's my 2 anti-structures. So again, try to think whatever is easiest for you. Some people want to think through, okay, I have my dash version, and then my wedge version, and then I attack from both sides. Be that person, if you will. This, to me, I think is the most pragmatic in terms of get the answer quick and get it correct. Cool. Yeah.
How do we know that the H has been added to the side with?
Don't. Wait, when we say the side, do you mean the left versus the right side?
Yeah.
Oh, it's because this deuterium is just like a hydrogen. So if we're looking at the carbocation here, this carbon is only secondary because the deuterium is not another carbon, whereas this carbon is tertiary. So which carbocation is more stable, secondary or tertiary? Tertiary. So that's why we make the carbocation over here the more stable side and the hydrogen's added to the other one. Yeah. At first I thought you were wondering why does the H add on a wedge, and it doesn't. It can add to both, and that's what the plus minus takes care of. Yeah. Yeah.
Just to clarify for the one on the left, the reason we don't have to draw another plus or minus structure is because whether that H is added on a wedge or dash doesn't matter because it's not a stereocenter to begin with.
Yes. Yes, exactly. So because there's only one stereocenter, then we only have two options. We have the OH on a wedge option and the OH on dash option. Totally. Let's talk about anti-additions. So, this second family I call the halogen anti-additions. It has anti in the title, so do you think this is syn or anti? Anti, there we are. So the mechanism for this one's fundamentally different than the carbocation. The carbocation is like a major way of thinking about alkene reactions. Then this one forms this cyclic structure that's kind of like an epoxide. And so this is going to be the second big way. So again, I kind of personify it because, you know, that's how we make molecules more interesting. So we have the pi CC attacking the sigma star XX. And so that's this arrow, and this is just a consequence arrow. Because we put electrons in antibond, we have to break the bond. But then, this bromine says, you're trying to attack me? I'm going to attack you right back. And so the lone pair on the bromine, or the chlorine, whichever one, goes and attacks the pi star of the CC, which causes the pi bond to break, which fuels this attack, and oh my gosh, it's a concerted reaction. Oh my god, concerted, everything happening at the same time. So you are like having a driving force for both sides of it. But again, I like to think about it as like, you're going to attack me, I'm going to attack you. We're both going down. So that's how we avoid a carbocation. We are forming two bonds at a time. Now, if our double bond's here and the thing comes from above, we make an up triangle on wedges. If it comes from below, we make a down triangle on dashes. We still have two options, either way. And then based on where our triangle is, up or down, that determines where our nucleophile is going to attack. So to think about this, let's go back to what we saw with epoxides. So epoxides form the little triangle here. And when we form these cyclic bromonium or cyclic chloronium ions, remember there's a positive charge on this halogen. And so it's going to react like the epoxides in acids. So our nucleophiles are going to attack the more substituted side, because that's the side with the more stabilized partial positive charge. But more than that, when our nucleophile attacks the more substituted side here, it's not going to attack from above, because remember, it's attacking a specific orbital. We need to break this bond, so we need to put electrons in its antibond. So if our triangle is going up on a wedge, then our nucleophile has to attack from below in order to actually get electrons in the antibond. So we're going to have our nucleophile added on a dash. So let's see that. Over here, when we are on a wedge, the nucleophile attacks from below, and now we see our nucleophiles on a dash over here in the product. And our halogen that was in the cyclic bromonium, cyclic chloronium, like little triangle, stays on the wedge, because that's where it was. For the version where the triangle is below, then the nucleophile attacks from above, so the nucleophile is on a wedge over here. And whenever it attacks from, like in this case, when it attacks from above, it just kind of shoves the methyl group down, because it says, I'm attacking from above. You are irrelevant now. So I would focus on mainly where the halogen and whatever the nucleophile end up. Work. So we get the anti-addition, we get the 2 enantiomer products. We're never going to get a mixture of 4 products for this one. So with this, our base cases here are we add Br2 or Cl2, they add 2 Cls or 2 Brs. But if we have Br2 and then we do it with water, who do you think is going to do the attack? One bromo boy or one of the billions of water molecules? Water molecules, it's just a numbers game. So it's going to be the one that does the outside attack. And what that means is we have one bromine from the original attack forming the cyclic structure. And then the other, the water, turns into an OH on the molecule. So overall, we call this a halohydrin. Halohydrins? I know her. Where do we know her from? Yeah, you were at that party that Mark threw, blah, blah, blah. Yeah, no, from lecture 7. She makes epoxides. If we add NaOH to this, she can turn into an epoxide. Bloop. Exactly. So they're all connected. I I can't remember if I've told this section in the last 30 minutes or if this was something I said in the other ones, but like going to exam 2 is kind of like watching a TV show. Have I already said this? No. It's like watching a TV show where each lecture you focus on a different cast of characters, and then you go on to different characters, and then the exam is like the series finale when you're like, all the friend groups know each other, they all go to the same school, and like they get to be like side characters in each other's story, and they all come together. But a lot more stressful. But it's kind of like that. Kind of.
Oh my god.
So again, this intersects lecture 8 reactions with lecture 7. So they're all connected. So here we are adding a Br and an OH, and the chlorine version, same thing, Cl and an OH, making our halohydrin. When we just add 2 bromines or 2 chlorines, we form a vicinal dihalide. Vicinal as in the same vicinity, di as in 2, and halide as in halogen. Vicinal dihalide. Last one is, we could do this instead of with water, we could do it with alcohol, in which case we have ROH, 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 and so on and so forth. Who will win, one bromo boy or one of the billions of alcohols? Alcohols. So it's going to go attack, and then it's going to get deprotonated. And so the things that we wind up with are we add the Cl, and now we have an OR added. And great, another way of making ethers. I'm so glad I know this. The best functional group. So good, so fun. And specifically, this is an ether right next to a halogen, so we call this a halo ether. Cool. So this is kind of the basics of the anti-addition. So I have a practice for y'all. This is from the skill builders, where it's a little bit weird of like, what if it's not the same halogen? What if it's an I and a Cl? Note about the electronegativity here, and also I'm going to give a hint. Who has larger lobes in the sigma star bond? So think about that as you are trying to figure out what happens. And then because this is a pretty short reaction, what I'm going to do is I'm going to write another reaction for you to try that I just made up. So we're going to take a few minutes to try these out. Howdy. So let's see how it went. So, antibonding orbital. Are we going to have larger lobes on the iodine or the chlorine? So the rule is, for the bonding orbital, we have more electron density around the more electronegative for the bonding. But for the antibonding, it's swapped. So you are going to have the larger lobe of the antibonding orbital on the less electronegative. And it's kind of like carbonyl-wise, so like this one's going to be a little bit smaller. So remember, on a carbonyl, we said oxygen's more electronegative, so that's why the less electronegative, the carbon, had a bigger pi star orbital. That's where we've kind of seen this a little bit before. So now, what we do is the anti-mechanism. So we attack our antibonding orbital. I'm just going to draw it to the eye, but we know it's going in the antibond. And then that's going to break the bond. And with the halogen, it says, you attack me? I'm going to attack you. So we get this three-membered ring with an iodine. So if we had a cyclic bromonium, cyclic chloronium, anyone want to take a stab at what this is called? Cyclic iodonium. Ding dong. Ding dong. There's a lot of syllable on that. I'm here for it. So we have this. We've kicked off a Cl. And then is she going to attack the more or less substitute side? The more. Remember, it's like epoxides and acids. When we have a positive charge here, it's making these bonds even more polar. So we have partial positives here. And we are going to attack the side that has the more stabilized partial positive, which is the one that's on the more substituted carbon, kind of like a tertiary carbocation. So we attack in, push up, and then here we have our Cl and our I. Is this a stereocenter?
No.
Is this a stereocenter?
No.
Do we have stereochemistry in the product?
No.
Ding dong. So is this molecule chiral or achiral?
Achiral.
Achiral? All of our terms? Wow. But remember, this is a question that we're going to be asking ourselves a lot with these alkene reactions because they have the potential to make stereocenters. Now over here, starts off doing normal things. I'm an alkene, I see a Br2, I make a cyclic bromonium, sure. And then, one option would be a Br comes in and attacks the more substituted side. But what else do we have on this molecule? Sorry, I breathed in really fast and then it made me have to cough. So, we can do an intramolecular attack. It's kind of like, remember if we have this and like an alcohol? We said step 2, an alcohol could come in and attack, and now the alcohol is just on the molecule. So it's even faster than an intermolecular between two molecules. So she's going to come and attack here, and that's going to make a 1, 2, 3, 4, 5-membered ring. And our 5-membered ring. And I'm just going to do this as an intermediate. I'm not going to draw the full mechanism here because I think that you can do the arrows for the Br. We form our 5-membered ring with the oxygen. 1, 2, 3, 4, 5. And then carbon 1, we broke this bond, but she still has kind of a dangly bit and a bromine. So on carbon 1, we put a dangly bit and a bromine. Now, is this a stereocenter? Yeah, because these parts of the ring are not equal. One is an oxygen, one is a carbon. We have this, and then we have a hydrogen. So we know that we are going to get both versions of this. We're going to get the version of this on a wedge, and we're going to get the version of this on a dash. And technically, we should even put our plus and minus here for this intermediate, because we could form the wedge version of this, or we can form the dash version of it. Cool. And then technically there's also going to be, like when it initially attacks, it'll be OH plus, and then you have to do a deprotonation. But I'm just trying to condense some of the steps. Yeah.
Checking for the intermediate, it's plus or minus because of the nucleophile oxygen if it comes from above or below.
So
Attacks from above or below.
this being, it's kind of weird. The plus or minus comes from, did we form the triangle up or triangle down? So it's like the plus or minus is about the journey we took to get here, not what's happening in this step directly. Yeah. Yeah. Cool. So, here we are. Let's see. Dun, dun, dun. Alcohol. So, we have one way of making alcohols from alkenes, which is our H3O+. What is weird about this? What do we not like about this? Here, we have all of our methyls in one place. Here, a methyl has moved. So what happened? A rearrangement, carbocation. Those are hard to control. So we want another way of doing the reaction where we can get the oxygen where we want it. Let's say we just want, the oxygen where we want it here. We just want the Markovnikov product of the OH added to the more substituted side. So the way that we can do that is we can use HgOAc2 with H2O and 2 NaBH4. And that is called the oxymercuranium. That's right. Oxymercuration, reduction. Oxymercuranium is the intermediate. So, let's see how that happens where we can do Markovnikov with no rearrangement now. Oh, I need to change my little box. I'll come back to her. So, HgOAc2 here, this mechanism is actually pretty similar to the dihalide one, where it's, I'm going to attack you in terms of the pi CC attacking sigma star HgO, and then we have a consequence error because we put electrons into an antibond, and then it says, you're going to attack me? I'm going back to you. So the lone pair on the mercury is going to attack the pi star CC. Yeah, the vibe of the anti-additions to me are very aggressive, where the carbocation is like, oh, grab a proton, what'll happen? I don't know, there's a carefreeness versus an antagonism in my head. But again, that's delusional. Here we are. So we can form our little triangle now with mercury, so it's a mercuranium ion. We can form it up or down, so we can indicate that with our plus minus. And then we have HgOAc2 and water on our arrow. So water can come in and do the attack. And because we have the triangle, just like we had for the other dihalide anti-additions, we are going to have this attack from the opposite side. So if our triangle is on the wedge, then we are going to add our water on a dash, and vice versa. So there's a deprotonation step here that I just left out just to kind of show clarity, big picture. But once we get here, we see we've added an OH and an HgOAc anti to each other, just like all the other triangle ones. Now, I put a skull here because she is scary. She's an organomercury compound, and she's the type of compound that is a neurotoxin, and in all the lab safety videos, it's like, when Dr. So-and-so realized that she got half of a drop of the organomercury on her skin, she knew she only had days left to live. There was no saving her. She was aware of her brain shutting, horror stories. So do you think y'all will ever do this reaction?
Never.
No. Do you think I would ever do this reaction? No. I'm far too clumsy. They would let me, but I wouldn't. So we need to get rid of her fast. And specifically, we want to add a OH and an H. So our second step, NaBH4 comes and replaces this HgOAc with an H. Now, Logan did a fake mechanism where it was just erase. But if we have to think about stereochemistry, it's a little bit more complicated. So you've seen NaBH4 before, right? What has she done in the past? Yeah, she's done the reduction of carbonyls to alcohols, right? She's doing something different here, and you're not going to be responsible for the mechanism. She does radical stuff here. So she doesn't function the way that you've seen her before. But when we do radicals, we are actually going to be fully breaking this bond. And then we have a radical here, which is kind of like having an empty p orbital if it can attack on the top or the bottom face. And so when we add a hydrogen, we're going to add both on the wedge and the dash. And then also we still have the plus minus versions for both of them, which is not in the sheet. I forgot to write it in. So, and that's from this first step here. We get the plus minus just from, did we form a wedge or a dash? So it adds anti after the first step, but then NaBH4 scrambles the stereochemistry. So overall, we get mixed stereochemistry at the end. We get both syn and anti. That's why we can get up to 4 products. 90% of the time, will you have to worry about that? Because will there be 2 stereocenters? Probably not. But I like to show you the complicated version, just so you've seen the worst. Now, one variant of this is, what if instead of H2O, we added an alcohol here in its place? Well, then we would go to this step. Instead of H2O attacking, ROH would attack. And what we would get is we would get an OR added. Yay! Yet another way of making ethers. I love life. I love life. They just sneak up on ya, the ethers. They're so fun. I also, for these family of reactions, I have the worst mnemonics of the entire class. So bear with me. So how to remember that if we want no rearrangement, we should use this mercury compound. I think about praying, please let there be no rearrangement. And then none of the current gods are working, so you have to go back and do the Roman Greek gods and say, Mercury, god of communication? Yeah, I think something like that. Messenger god, Mercury, help me out, no rearrangement. And Mercury says, no one else is asking for anything, I got you. Here we are. And then how to remember that the NaBH4 scrambles the stereochemistry in mixed. I don't have a way. So, yeah, I'm just like, NaBH4, she's not doing her normal thing, and so her energy is kind of like, I'm so random, and then scrambles things. So again, really smooth brain way. Yeah. No, it's not going to do the same way. Yeah. Mm-hmm. So we have this, but now let's say, what if we wanted yet a different alcohol? What if we wanted the version where we put OH on the far side here? Is this our Markovnikov product or anti-Markovnikov product? Yeah, because if we are adding an H and an OH, it looks like we're adding the more electronegative thing on the less substituted side, anti-Markovnikov. So this is what we need the third reaction for. So our third reaction here is hydroboration oxidation. So it's BH3, THF, and then step 2 is H2O2, OH minus. And you could write NaOH. When I learned this in 2015, it was H2O2 OH minus. I said I'm not changing now. So with this, we can go and look at it. The way it works is it's very similar to some of the other reactions that you've seen, where you have your pi CC. Now, instead of attacking the antibond, it's just attacking the empty 2p orbital on the boron. And then you get the sigma BH bond attacking the pi star. So it's still a concerted reaction, but it's only 2 arrows because you're not putting something into an antibond. And you've also seen a sigma boron hydrogen bond act as a nucleophile or donor in the sodium borhydride reaction. So when we do this, what we get is a syn addition, because if our double bond's here and BH3 floats in from the top, both things are adding on the top. So syn addition. And then the thing that's weird is if we just look at this step, boron is less electronegative than hydrogen. So did we follow Markovnikov's rule here? Did our more substituted thing did our more electronegative thing add to our more substituted side? Yeah, hydrogen in this case is more electronegative than boron, and it added to the more substituted side. So we followed Markovnikov's rule. But wait, I thought that the purpose of this is anti-Markovnikov. What's going on? And it comes in our second step. Our second step, you're not responsible for the mechanism, but it's really cool. It replaces BH2 with OH. And it does so in a really coordinated way, so it stays syn at the very end. But now, if you looked at this, and it was like, oh, okay, I added 2 things, does this look Markovnikov or anti-Markovnikov? Anti. because a more electronegative thing is added to the less substituted carbon. And so overall, this reaction scheme makes something that's anti-Markovnikov, but it does technically follow Markovnikov's rule. So that's kind of the nuance.
Is this the one where Logan was like, it does the sneaky thing by substituting a less, like, oxygen is more electronegative than...
Yes, this is the sneaky one. And this is fully an FYI box. You can completely not look at it if you're not interested, but it just gives some more information about this because it's kind of cool chemistry. Like, this is the second step mechanism in case you were curious, but also I'm not going to talk about it. It's not testable, so it doesn't have to exist. Now, are you ready for the worst mnemonic I've ever come up with? So, hydroboration oxidation, HBO. HBO is a streaming service. On streaming services are movies. What's a movie? John Tucker Must Die, the comedy from the early aughts about a guy named John Tucker who like cheats on these girls and they realize it and then gang up against him and get revenge. So in that movie, those girls, they are anti-John. They might also be anti-Mark, anti-Markovnikov. So, thinking through all of this, if I'm trying to do anti-Markovnikov addition of an alcohol, I think anti-Mark, anti-John, John Tucker Must Die, HBO, hydroboration oxidation, which is crazy, which is fully crazy. And what's worse, someone in the 8 a.m. section immediately Googled it and said, it's not on HBO. And I said, stop, I don't care. Like, this is just how my brain worked with this. Because otherwise it's just not super sticky to me. Like this, without this, which is absurd, this is very boring. The other thing I like about this mnemonic, remembering it with HBO, HBO is like the uncensored like TV network. And so it shows like graphic language and like nudity and things. So there's a lot of sin, like S-I-N, that's on HBO. And it's a sin reaction, S-Y, up. So... Again, I feel embarrassed every time I say these two mnemonics because these are the most like smooth-brained ones I've ever thought of. But here we are. Yeah. So let's try out these 3 quick practice problems together. The first one, you're going to do the organomercury reaction. And the question in the problem set doesn't have stereochemistry, but I'll indicate stereochemistry with this like plus minus that's formed. Second one is doing hydroboration oxidation, but now it's doing it with deuterium. So like, what's a D, what's an H? Remember, they function very similarly. And then the last one is like a little small mini synthesis of just like a couple steps that's on a challenge problem of how do we get to this bromine being added on the end. So I'm going to give you a few minutes to work on that, then we will go over it. Welcome back. Okay, so I put some answers up for the first two. For the first one, it's just straight up the Mercury one, like it's just reproduced the arrows. There's not anything super crazy. The only thing is just knowing that here we could form the Mercury ring on wedges or dashes. And so that means that we have to put our plus minus here. We can form the wedge version or the dash version. In the product, there's only going to be one stereocenter, so we still have our plus minus carried through in all the steps. Yeah. Then, second one, BD3 functions just like BH3. So we do this kind of reciprocal attack. You attack me, I'm going to attack you. A deuterium is added here. But then in step 2, it replaces the BD2 with OH here. What if I had done BH3, D2O2, NaOD, then this would be an H, this would be OD. So it's just tracing where these hydrogens and like oxygens and things come from of like which step. Cool. So let's talk about this last one. So overall, what does it look like the two things we added to the alkene are? Like in terms of like the what?
Like H and Br.
Yeah, we have an H that seems to be added here in a Br. Is it Markovnikov or anti-Markovnikov? Anti or more electronegative thing, bromines, added to the less substituted carbon. So we need this anti-Mark. So HBr doesn't work, just normal HBr, because HBr is going to create Markovnikov product. And more than that, it has a carbocation next to a strained ring that's going to rearrange. So she does not work. Then you did learn a radical mechanism to do anti-Markovnikov HBr, but it's going to have the same issue as a carbocation, where when you put a radical here, it's going to ring expand in order to make a more stable molecule. Just like we do carbocation rearrangements, we have some rearrangements that happen with radicals that we will talk about in section 9. So that doesn't work. So what's our old reliable for anti-Markovnikov? HBO, anti-Mark, anti-John, John Tucker must die on HBO, hydration oxidation. Rolls off the tongue. So we use BH3, THF, H2O2, NaOH or OH minus. So that makes our anti-Markovnikov alcohol. And then, how do we go from an alcohol to a bromine? Where have we seen that before? Making an alcohol leave. Ooh. PBr3, lecture 7. This is again where you say, oh, they're all in the same cinematic universe? Wow. Oh, wow. They've met before? Yeah, they've met right here. Ding dong. And you bore witness. So now, the last practice that we are going to talk about, this practice number 4, it is a tricky stereochemistry problem, and historically, no matter how we have taught it, no more than about 50 or 60% of the class gets it. Mostly just because it's a lot of work for little payoff. And so I'm going to tell you right now, like I'm going to teach you how to do it, we're going to go through it, but at the end of the day, you might just be like, I could do that, but that's going to take me 4 minutes in an exam. I'd rather just take a 2-point deduction and like go with God, make whatever choice. But I'm going to show it to you at the clearest way I have ever seen it done, you know? So let's look at this reaction, and this is going to be like our H2 palladium on carbon, right? So what are the what, where, and how of this? So what are the two things that are added in H2 palladium on carbon? H and H. And so D2, it's going to be? D&D, Dungeons and Dragons. Wow. So we've added 2 Ds. Then does this reaction add syn, anti, or mixed from lecture? Syn. It's because palladium on carbon, it's a surface, a flat surface that you're reacting against, so they both have to react on the same side. And then is it Markovnikov or anti-Markovnikov or Markovnikov? Do you know what I mean when I say that? Oh, maybe, again, I forget what I say in the sections because I just am in this room for 6 hours and, you know, it all blends together. So there are some reactions that I call Markovnikov, mostly because which one's more electronegative? Br or Br? There's not. So saying is it Markovnikov or anti-Markovnikov doesn't really make sense. It's a bad question. But instead of have a third thing to memorize, I'm just going to be like, it's normal, Markovnikov. So Markovnikov is kind of how I refer to it. So this H2 is Markovnikov. So with that, we know these details. And we know here are the two deuteriums that were added. So we know the double bond was here, right? But the issue is we have this, or we have this. We have two options. One option where the methyls are trans to each other, one option where the methyls are cis to each other. And we need to determine which one it is. So this whole process that we're about to do is going to be to try to figure out which one it is. And again, on the exam, you could just take a guess and 50% get it right. Other 50%, it's a 2-point deduction. It's not the end of the world. There will be exactly one of these on the test, so it is going to come. But let's see what it is, and then we'll see if it's worth the time. So we know that this reaction added syn, so somehow we have to visualize our product molecule where we see the synness. We see the two deuteriums added in the same way. So here, do you see how one's on a dash, one's like on in the plane? So it's kind of hard to actually see it as syn. So there are several ways you can do it. One way you could do it is redraw the molecules so that they're both on dashes or both on wedges. That's fine, but I think it makes the second step of this process a little bit harder. So my preferred way is, if you know it's syn, rewrite the molecule so that your two things are either in the plane both up or in the plane both down. So like this. So we already have one down in the plane. So let me try to redraw this molecule. So both of my deuteriums are down in the plane. So this right carbon over here, we don't need to rotate it at all. So it's methyl, it's on a dash, and its hydrogen is on a wedge over here. That stays exactly the same. But then for the other one, we have to do some rotation. So in this figure, imagine the blue is the deuterium. So this is the deuterium that's in the plane. This is the deuterium that's on a dash going away from you. Is that okay? So that would make this red one coming towards you the methyl. And I'll kind of label it here red. So it's on a wedge coming towards you, and now the deuterium is away. We want to rotate this deuterium so it's in the plane of the page. So is that methyl going towards you still? So should it be on a wedge or a dash? Wedge. It's just now it's an up wedge instead of a down wedge. So our methyl is up and on a wedge, and then that's going to rotate our ethyl onto a dash. And we can kind of see that here of like, this is the version where the deuterium's away from you. This is our ethyl that's like up and in the plane. And if I rotate the deuterium here, now the ethyl's going away from you. So it's on a dash. So with that, once we have drawn it this way, can we clearly see this as syn now? Like we see they're both added on the same face. So once we have that locked, then the thing that we can do is anything that's on wedges together, they're going to be cis to each other on the alkene. Anything that's on dashes are going to be cis to each other on the alkene. So we have the ET and the methyl cis to each other. And then we have the hydrogen and the other methyl cis to each other. So that is how we know that this is the starting material that generated this product and not the other one. So much work for just that. It really feels like not worth it in my mind. And like when I did organic chemistry, I saw this and I said, nope. And I just, again, doing this correctly and rotating molecules on the test, it just takes a lot of time. I would use your meso little molecule or 2 stereocenters to help you on it, because again, there will be one on the test. But the other thing I want to show you is, so now imagine we have the 2 deuteriums down in the plane here, and the red ones are going to be the methyl. So one methyl is coming towards you, one methyl is going away from you. Do you kind of see this molecule as a redrawn version here? Deuterium's down, one methyl towards you, one away. Well, when we do this, what we can do is we can think about folding this back into what the double bond would look like. And do you see how the methyls are trans to each other now? One's on top, one's on the bottom. That folding is mimicking the actual kind of reaction of it started as a double bond, and then this double bond, one side popped open, and we added two things on the same side. Which I think is kind of cool. And if you're not afraid of bending your model kit, and if it won't break, then it's kind of fun to play with. But I'm going to do all of these with you just because I think you need to see it a few times, and then I'll let you kind of practice it on your own with other things on the problem set. So, for this one, I2, what two things does it add? I and I. Now, is it Markovnikov or anti-Markovnikov or Markovnikov? Markovnikov. And then, is it syn or an anti-addition? Or mixed? The halogens are always anti-additions. Because remember, it's going to form the cyclic, in this case, iodonium ion. And then it's going to do a backside attack, so it'll be anti. So we need to draw anti. And again, if we want to do this in the plane method, then we want our R1 and R2 to both be in the plane, one going up, one going down. So the other way of doing it is R1, R2. So, hey, well, we kind of already have that. Our eyes are in the plane, one going up, one going down. So we can keep everything the same. We don't have to rotate. So this is a nice question. It won't be this nice on the exam. Unless we need to make the exam easier. In that case, we would do that. I need to write the exam. I fear. So now, when we see this, we see the two things that are both on wedges are the ethyls. So that means in the alkene precursor, those need to be cis to each other. And then the hydrogens are cis to each other. So we have this as the precursor versus the one where the ethyls are trans. Last one. Hydroboration oxidation, what two things do we add? H and OH, I heard whisper. Markovnikov or anti-Markovnikov? Anti-Markovnikov, which you know from your great mnemonic. Then, is it a syn addition or an anti-addition? HBO has all that syn. So, with this, we know where our OH is, but we have to figure out which side the H was on. So it could have been here, or it could be here, right? Both are options. If we did an alkene here, do you have a more substituted side to that alkene? No. Both of them have one thing on it. So this is not going to be a selective alkene to start with. But if you put your double bond here, is one side more substituted than the other? Yeah. Are you adding your OH to the less substituted side? Yeah. So we know that we are talking about this hydrogen here that's on the wedge. Okay. So if it's a syn addition, we need to draw it so that they are both up and in the plane, or both down and in the plane. And so we have to rotate both sides now. So if this OH is the red here, and it's away from you, and we want to rotate it up in the plane, like this, here, this is what's originally on a wedge up here. So we originally have a hydrogen up here on a wedge, and then if we rotate the OH just up in the plane, a little 60-degree rotation, that wedge is still wedging. It's just wedging down. So we have our hydrogen down on a wedge, and that's going to bump the ethyl to a dash. Then the other side, it's a little bit easier of a rotation. So do you see how we want the H to be up and in the plane over here? And we already have a bond angle drawn there. We're doing a 120-degree rotation. So this can be kind of like when we're doing the R and S redrawing, where you can just be like, okay, this one goes here. This one goes here. Oh God, that looks horrible. Let me try drawing it one more time. how do I want to see it? This one goes here. This one goes here. This one goes here. So the H goes up and in the plane. Then that's going to rotate this one in the plane back to the dash. And then that's going to rotate the methyl that was on this dash up to the wedge. And again, you can also do it with the model and rotate and try to see it. But now we have officially shown, hey, it looks thin the way we've drawn it. So now we can compare the dashes and wedges. So we see the ethyls are both on the dashes and the methyl and hydrogen on the wedge. So we know the ethyls need to be cis to each other in the starting material. And then we know the methyl and the H here. So we have methyl H. Bum bum. Ding dong. Again, it's a lot of work. I think everyone can do this, but the real judgment call is how quick can you get at it to where you're doing this? Because typically it's going to be in a box problem like this where you're predicting reagents, and there will also be another 1 or 2 reactions on the line reaction for the box problem. So it's just kind of a lot of work, but ding dong, you can do it. Or you can take the 2-point deduction or just guess. Either one. With that, I'm going to keep plowing ahead just because I want to touch base on everything. I think we're going to run short on time for the vid egg. So, So we have been up until this point talking about the simple reactions, the ones that are very mechanism heavy. Now we're going to talk about some of these complex alkene additions where we much more care about line reaction level. We care about being able to draw the product. We care about some nuances with synthesis, box problem stuff. So the first one is ozonolysis. Ozonolysis is a beautiful, beautiful reaction, and you are going to see it on synthesis, a heavy hitter. So specifically, ozonolysis is great at if you have a double bond in a ring, specifically just an alkene, not a whole aromatic ring, arene ring. It can chop it in half and split it open. And so if you ever in a synthesis need to go from, hey, I'm a ring to I'm no longer a ring, ozonolysis probably was your girl. The way it works in terms of a fake mechanism, because you don't need to be responsible for the real one, is I imagine O3 is little oxygen scissors that goes and cuts double bonds. And so what's it going to do? Well, it's going to go and find a double bond. And then on both sides of the double bond, we are going to make sure we have a double bond to O in its place. So it chops it in half, puts on oxygens. And then our second step for ozonolysis is where we have some variation. So if we have DMS, dimethyl sulfide, we consider that our reductive conditions. And under reductive conditions, when we chop in half, add the double bond O, we're done. But if our second step is H2O2, that's our oxidative conditions, and we have one more thing to do, which is, if there are any aldehydes present, we need to oxidize them all the way to carboxylic acids. And that's it. So not too bad. We do oxygen scissors, and then oxidation, we take aldehydes all the way to carboxylic acid. So can you try these two really quick of the disconnection getting the product? Remember, this reaction does not affect aromatic rings. You're going to learn about the chemistry of aromatic rings tomorrow, lecture 9. So how'd you do? So for a DMS version, we just chop along the bond, put carbonyls in its place. And then we see one of these with an aldehyde. So in the oxidative H2O2 conditions, we just take that all the way to a carboxylic acid. Then for the bottom one, we chop it in half and we get ketones for both of them. So the oxidative and reductive conditions look exactly the same. Like you can't oxidize a ketone all the way to a carboxylic acid here, just because you'd have to break a carbon-carbon bond, and that's a little bit more difficult. There are ways you can do it, but those are the big guns. We don't get to the big guns in this class. Does anyone want to know about the big guns? Cool, never mind. So, ozanolysis, that's the first one I wanted to touch on. Osmium tetroxide, again, a light touch on it. She makes a vicinal diol, two OHs that are neighbors to each other. Now in lecture 7, you saw another way of making a vicinal diol. How do we make it in lecture 7? So that's, no, that's going to be this way it's coming up. But lecture 7, epoxide. So we could have done an epoxide, and we could do a base version, or we could do an acid version of this. And then we just add in like H3O plus or OH minus, and it depends on the stereochemistry of the products exactly. But yeah, we could make this from an epoxide. So when we do that version, remember with the epoxide, when our nucleophile attacks, it has to attack from the opposite face. We're going to get an anti-vicinal diol that way. But when we do it with this new reaction, the osmium tetroxide, it is going to make a syn vicinal diol. And it's because both of those oxygens are coming from this osmium guy, so they have to be on the same face. So that's kind of like a niche argument, but it's something that is often appears on tests. Like it's a detail that we like, because if we have a syn vicinal diol, what reaction is this? So, oh my god, lecture 3, I'll remember her. That feels like a decade ago. Wow. Back in my day. Like, wow. So syn vicinal diols can form acetals, which is a really great way of like linking up lecture 8 and lecture 3. And if someone was writing a test, they might be like, how could I link up lecture 8 and lecture 3? So you'll see it on the practice exams. This appears pretty often of a vicinal diol is formed, and you have to notice whether it's syn or anti to know if it came from osmium or epoxide.
How are we supposed to know if it's syn or anti?
You will see it in the product. So in the product, if they're both on wedges or both on dashes, that's syn. And then if one's on a wedge, one's on a dash, it's anti. Yes, because otherwise, if you're controlling it, then you can choose which one you want to do. Yeah. Last one I want to touch on here is epoxide formation. This is just my favorite reaction in OChem 1, MCPBA. I just think she's neat. I really just do. I like it because it's a little quirky. You have this oxygen bond. You do 4 arrows in one step, and then you're done. She stands on business, it's a little like kooky, and gets out of there. Sound like anyone else you know? But it makes an epoxide directly from an alkane. So we could do our 2-step way of, we could form a halohydrin where we do like blah, OH, and then Br, and then this, and this would be with Br2 and H2O. And then you could use NaOH. That's one way of doing it, or you can do it all in one step with MCPBI. So there's not really a reason to do one over the other. Just use MCPBA because she's cool. I don't know. So that's all I want to talk about with that. And I do realize that it is 2 o'clock, but I did start 7 minutes late. So I'm going to keep going. Feel free to leave if you need to. But the last big topic I want to talk about is the Wittig reaction. These other complex additions, I'm just not going to really talk about because they're mainly line reactions. One of them has no mechanism. The radicals one I'll talk about in section 9. So Last one, the Wittig reaction. Wittig reaction is powerful. You are 100% going to see her on exam 2. She is a way to make a carbon-carbon bond, which up until this point, you only know very few ways of doing it. You know, like organometallics, like Grignard or alkylithium, organocuprate, attacking carbonyls or anones. You know, I guess you know like an SN2, like a cyanide CN, that carbon is a nucleophile that does a backside attack. And then this is way 3. So like you don't have that many options, and we're not going to teach you many more options. So it's a really powerful way of making both a carbon-carbon bond, and also it goes all the way to make a double bond at the same time. So the two things that come together in the Wittig reaction are a ketone or aldehyde, and this new functional group called an ylide. Ylides are molecules where we have a negative charge and a positive charge right next to each other. So this would be like a phosphorus ylide. There are also like sulfur ylides and other things, but we don't care about her. So what happens in the Wittig reaction is the base part of the carbonyl and the carbons on the ylide come together and get fused with a double bond, a carbon-carbon double bond. And this is kind of interesting because, one, you're going all the way to a double bond, but two, you preferentially form the Z alkene. And for this class, we don't really get into why that happens, but remember back to think of the other way of making carbon-carbon double bonds, which is eliminations, right? We rarely formed the cis one. We would always form internal trans as our favored with like Zaitsev's rule and everything. And so to get one where the cis or zizamzide version is favored, like that's going to be a little bit harder to do outside of the Wittig reaction. So if you see a cis or Z alkene, you should be thinking Wittig. The other thing that it's good at doing is you can make terminal alkenes pretty easily with these. So remember, if part of this came from an ylide and part of this came from a carbonyl, we need to chop this in half. And if we have a terminal alkene, we have one carbon alone on the end. So if we have a lone carbon as a carbonyl, that could be one option for this plus this ylide is going to get our terminal alkene. Or if we chopped it up and we made this side the ylide, then we can have a CH2 on the ylide, and then it's just a one carbon ylide. So it's good at making terminal alkenes. Why are terminal alkenes hard via elimination? It's on the screen. Zaitsev's rule. Zaitsev's rule says our internal alkenes are favored. I know it's so long. It's such a long day. So the internal alkenes are favored with Zaitsev's rule. So terminal, we would have to use like tert butoxide or bulky base to get our like Hoffman elimination. And it's more complicated. Versus it's really easy to make terminal alkenes with the Wittig reaction. So let's talk about the actual Wittig reaction. I'm not going to go through it. It's super, super detailed. The ylide is a nucleophile, attacks carbonyl electrophile. It associates and forms this weird four-membered ring. And then we have a box. So I call this the Boxy Boy reaction because it does this like cool like little, it feels like voguing or something. Like it forms this box. And then she says, let me snap apart. And then splits into two molecules, which is just kind of fierce. So the mechanism, it's a great mechanism question. It's really helpful for synthesis. But this mechanism isn't super long. The thing that makes it a little bit longer is we don't know any ways of making ylides. We know how to make ketones and aldehydes now. So let's talk about how to make an ylide. We start at an alkyl halide, and then we add PPH3, which is going to do an SN2 attack here. So let's think about what that means. Do you think it would be really easy to make a tertiary ylide? No. Why would a tertiary carbon be horrible at this? Because it's an SN2 attack. It's going to be sterically hindered, right? It's also the thing of if you tried to make a tertiary ylide, like in the second step, you have to deprotonate it here. There wouldn't be a hydrogen to remove. So we can't do tertiary. Secondary ones are going to be hard because it's really bulky. So primary or methyl are the best ones to do for ylides. And then once you've added this PPH3, she now has a positive charge. And then you use N-butyllithium just as a strong base to deprotonate this deprotonate this carbon over here. And then you are left with carbon with a minus charge. So that is how we form our ylide. The very last skill is thinking through the disconnections here. So when we chop a double bond in half, we want to be able to think about our options of making one side a carbonyl, one side an ylid. So option number 1, let's make the bottom part of this molecule into our carbonyl. Well, then the top part is just this single carbon with 2 hydrogens, right? So our ylid is going to be CH2 minus, and then you attach on a PPH3. So that's option 1. Option 2 is we could have swapped which one was the ylid, which one was the carbonyl. So now what if we make the bottom part the ylid? So we just put a PPH3 where that double bond is, and then we do our charges. And then the top one, the CH2, becomes our carbonyl. So now the question becomes, if we have these two options, which one's going to be the better option for doing the Wittig reaction, making the Wittig? And it has to do with our ylid. Which of these, option number 1 or option number 2, is a easier ylid to make? 1. Because option number 2 is a secondary carbon. So to make that ylid, you'd have to do an SN2 on a secondary, which is slow. Whereas this is a methyl, so it's going to be really fast at SN2. So this is going to be our preferred version for our ylid. I have another practice of doing the disconnection, and I have a practice connecting them, but because we're already over time and everything, I'll go ahead and stop it here. If you want to try it out, you'll be able to check it in the section annotated notes. But thank you all for coming to section. Oh my god. Wow, thank you. Gia, praying for my dad.